Okay, let's get started. So we were in the midst. So welcome to lecture 8. We'll continue our discussion on parallel repetition theorem in the first part of the lecture, and the second part will go on to hardness of max-free limb. So recall we were in the midst of proving the parallel repetition theorem. In particular, we wanted to prove from last time. This is the one wanted to prove the following number. Okay, and the way we had done this was we were going to generate a common randomness. So once again, let's see. Yes is a bunch of coordinates. These are sort of the one coordinates. And we're going to define some common randomness, common random string or random variable for the two provers. And it consisted of 3 parts. The first part was answers to coordinates in S. So this is AI, BI, this collection for I in S. So what we in short call AB, restricted to S. Okay, we're going to give this. Next part was the questions in coordinates S. That was xi, yi, I in S, as x. Then we should be just started. The random questions coordinate in S complement. In particular, we define this for all I not in S complement. We had defined VI to be uniform random drift. For the uniform random, for every coordinate not in S, we had tossed a coin to decide whether you're going to give Alice's question or Bob's question. And then Ti was the random variable, which was xi if Vi is 0 and yi if Vi is 1. And this set, I'm going to do VT, the S complement was this. So this was the common random string that the provers were going to jointly sample. And we had called all of this together as R last time. I'm going to change notation a little bit. I would like to keep the answers and the questions separately. So we will call this guy C and all of this guy R. So R, previously what was R? What was R is now being written as R and C. So R just refers to either the question to the fixed coordinates or a random question in the other coordinates, and C refers to this one. So just a note, last lecture R included. And what were the properties of this R? Properties of this joint random variable RC. The first key property was the fact that if the two provers had the copy of RC, had a variable sample from RC, given an x of x, prover x given prover A P1 given just the x first question and prover B given the second question could just fill up the remaining coordinates on. So what they could do is they could, so you look at this joint random variable, you looked at x, y, the entire random variable conditioned on xi being x and yi being y, and the event ws has happened, and r equals r and RC equals some small c. This random variable split off into a product random variable xi equals x and ws and RC equals c cross y. This was the property of the random variable. This we had discussed last time already. So this says that if the two provers had the copy of the random variable, had a joint copy of RC, then using this RC and this x, small x and small y, they could go ahead and get their K questions.
So this is because conditioning a product distribution on a rectangle keeps the product distribution.
What?
Conditioning a product distribution.
No. Why will the conditioning of product distribution?
So once we fix the questions of the coordinates in S, product distribution.
Once you fix the question, then the problems. No, not prior. Why? No, the answers. So because the answers are going to correlate like anything.
No, but once you're saying that the questions are in S at this, just further conditioning on the fact that Bob's pupil is a certain subset of X power and analysis pupil is a certain subset of Y power.
No. So not just that, you have to do several things over here. The fact that WS has been WS is the fact that you're saying it's 1 on the coordinates is possibly putting in a lot of is going to put in a lot of dependence between the two Alice and Bobs.
So, but if you condition on the specific questions they ask for S, then just if you just condition on that, then it's a product distribution between Bob's distribution and.
No, it's not. No, because if I just conditioned on questions, it is. But the whole point is I'm conditioning on WS, and that messes up things like anything. WS is the fact that they have 1. That means the answers, and the answers which they have got, the answer is a function of all the K questions. So
so I think there was one thing here. A product, I mean a product of Bob's, mu Bob cross mu Alice, not mu1 plus mu2 plus.
It is, but it is not just because you factored on the question. It's because of the whole nature of this random variable. I don't see how it's just done. So we discussed this last time. So WS causes conditioning like mad. Now you are going to go, because to remove the conditioning on WS, you give out the answers on the 1 coordinates. Now, once you've given the answers on the 1 coordinates, the WS is just a function of the is a function of the questions and answers. Therefore, once I give R and C, either WS happens or WS does not happen. So you can only restrict your focus on RC such that WS happens for this event. So now your WS drops out of this, but even then they are correlated because the answers to the coordinates in S heavily depend on the other question. Okay, prover is not this one, but now now you are going to use the fact that R has been built up this way. That is, for every other question, you are revealing one of the questions. Therefore, the only guy that it has to only sample from the corresponding marginals each time.
Okay, so
is
it incorrect if I interpret it in the following manner? Let's say I have conditioned on the answers that Bob and Alice give. To the S coordinates. So now this conditional distribution splits into mu bob takes of mu Alice.
No, it does not. No, it is because I'm further giving the random variable this R. What you said would have been true if what you're saying would be true if it without just giving C.
Yes, I'm telling just giving C here.
Just giving C, this is false. I don't think it's not true. The proof would be much easier if I just give C. How is the thing splitting off into a product distribution? So this we had this picture from last time. So
Okay. So original distribution is not product.
the original distribution is not product. So the green part is given to us, and you are giving also so what's been given in the random RC is the green part.
Okay.
This one, and I'm giving you two such parts. So now I'm claiming I can generate these two from Alice can generate this from this. She doesn't need to know this to generate.
Okay.
Yeah.
So okay.
If the original distribution was a free distribution, then I believe this, but the original distribution is not a free distribution. Even that I'm not fully sure. This you need to stare at this, but once you stare at this, I think it should be fine that this is.
So in the original distribution, you're sampling an edge. That's why it's not a problem.
Yes, he is sampling an edge. Okay. Okay. So this was proved last time, or observed last time, whatever. By the way, this is Rasborosis. This is Rasborough split. This is where this is the same idea which Rasborough used in his disjointness thing. Ras credits Rasborough for coming up with this choice of R. And it's the same thing which Rasborough had used in there. There it was easier than this. Here it's a more subtle argument, but it's the exact same reasoning to show why this product happens. But given this, now it's unclear that the two provers have the sample RC in them. This is all true if they had R and C with them. So now you want to show that there is the true RC distribution conditioned on xi equals x and yi equals y and ws. So somebody who knows x and y knows what is the RC sample that they're going to get. You want to show that this guy is close to RC. Alice can generate it just with her view of the world. And also, Bob can generate it. The second prover can generate it from his view of the world. So this will be an epsilon I, and we want to show expected value of epsilon I naught in S is small.
So this is small x sample according to capital X or the conditional.
The capital X. So technically, this is not because here it's unclear. So what you are stating is the following. So what you want to show is I sample an xi yi. So I'm going to write, this is the notation I'm going to follow. First I'll sample an xi yi. And then I want to, then this is how the so let's look, there are three parties here. One is Alice, one is Bob, and one is a third party who knows all information. So we're going to come, so I sample xi yi. So the true, so what's going to happen? The true thing is going to be, I sample xi yi conditioned on ws. Then this is the honest third party, and then that honest third party is going to sample an Rx conditioned on xi, yi, and ws. So this is in some sense. So let's write it this way. So the party who knows all of them, he gets a sample of xi, yi, ws. What I meant to say, we are looking at this sample xi, yi, r, c, ws. This is the distribution we want to look at. This is not the distribution in which xi, yi is sampled according to mu. Here xi, yi has been sampled according to this. But this distribution, I can write it this way. This is identical to first sampling xi, yi conditioned on ws, and then sampling RC conditioned on XI, YI, and WS. This is a notation I'm following in this one. That is this. But now we showed last time, I'll recall the claim that XI, YI condition on WS. This thing is almost the same as the distribution XI, YI for a random coordinate. So I'm going to say this is okay. So we are actually working with this. This is the event which we care about. But it looks like this event because of the reasoning we did last time. Okay. So this is what occurred. This is what the party which knows both information does. The party gets both XI, YI, and then using that XI, YI can sample RX, RC this one. What we want to show, so basically we need to prove this. So what we want to prove is this quantity is actually close, let's say some delta I to XI, YI, RC, just XI and WS. This will tell you that Alice is able to generate RC herself, and a similar thing you'll have to say for Bob. And then you use the correlation sampling lemma to say that all three parties get an identical copy, get the same copy with. So you will first show delta I, and you will then show similarly XI, YI, RC, WS is not close to. Similarly, here I want to show this is YI, and then there's an error of 2 delta I plus epsilon I in which the things generated by the two parties is the same as the same copy, and this will complete the proof. If we manage to show what is in purple, we would be done. That's the goal for the rest of the lecture. Not less today. Yeah, okay. So let's just recall that statement. Today we'll prove purple. And what was the KL divergence with from last time? So let's just pull it up from last time. It was this fact. From last lecture. It was this fact that if you had a bunch of events U1 to UN, which were a product distribution, and E was some you had a bunch of you had n random variables U1 to UN, which were a product distribution, and E was an event which was not too small an event with. Then, if you look at the expected L1 distance between UI conditioned on E and just UI, where UI on a random coordinate I, this is a very small number. Provided probability of E is not exponentially small in n, this will make this a very small. Okay. So in today's notation, so we'll write the conclusion. Yeah. So we'll write the conclusion. The way what's the conclusion? What here is we'll use the writing it in follow notation as this with whatever is the conclusion of the lemma. I'm going to write it as UI conditioned on E. This epsilon I close to UI, where expectation for I of epsilon I is less than or equal to square root D over M. That's one way of writing what's written above. There are going to be so many such expectations going on in the picture. So I'm going to write it even more. This one, what I will then do, this is one succinct notation. Another succinct notation I'm going to write is just UI conditioned on E square root D over N, and just put. So that is just stating that there is an error epsilon I, and then over the approximate sign, I'll put the random variable over which I'm taking expectation, and I take that epsilon I over that expectation. That's what I get. This is just short for that. It will just be convenient. We are going to keep doing this over and over again. Fair enough? Okay. So you recall this lemma from last time. And we proved this using KL divergence, using the definition of KL divergence and Pinsker's inequality. I want to see two extensions of this inequality, and I'll state it without proof, and it should be almost obvious extensions of above proposition. First extension which I will be talking about is the following. Suppose we had the form. I should actually just written code. So suppose we had ran U1, U2, UN were certain random variables, and we had one more random variable R. So these are a bunch of random variables, and E is an event. And we had the following for all R which is in support of R, we had that U1, U2, UN conditioned on R equals R is a product distribution. So I don't care whether it was product before, but after conditioning, that's the situation where we are in. So after conditioning, it becomes a product distribution. This is, and furthermore, such that for all R in support R, we had that probability of E conditioned on R equals R was greater than 2 power minus. So basically, this says that if you had condition on the event R equals R, this is, and then looked at the world going on, this is exactly the previous problem. R is some random variable for now. I think it's going to be the same R which we will be talking about, or some slight modification. It will be almost the same R. So then I want to say then I want to say UI conditioned on RE and UI just conditioned on R is also has the same feature. And this is just one convexity argument. This is true for every R in R. There will be a probability of R equals this one, and there will be a convexity to push that thing inside. So this should be trivial from what we have. We will. So this should be fine. The proposition this is 1, 1. I'm going to make a further modification to this. As far as this should be clear. Let's do. Here I'm going to put another event C, another random variable C. Okay. What I want to actually talk about. And I have this. So I'm going to add one more thing to the hypothesis that the support of C conditioned on R equals R and the event E is always less than 2 power H for all R in support of. That is, I'm going to condition this is C is another random variable that has this feature.
But I think changed in the conditions 1 and 2.
Nothing's changed. I have just copied that from before. By the way, so this I could have written it this way too. I could have written this as R and an R. Put it on either side, that would not have affected things. Sorry, I should have put it here. Here, what actually should have put with an R conditioned on E. Here also I put an conditioned.
We are giving the same copy of R.
Where?
The UI position of R position.
So strictly speaking, the way that should be viewed is first I think I should write it the other.
R position is the linear position.
I should write it this way. There's an order over here. UI conditioned on R. So technically speaking, what the stating is the second UI actually I should condition on R and E. I'm not doing it. The design, forgetting that random variable and just forgetting the random variable, forgetting the event E has happening, conditioning you only from the fact that R is a particular thing, and still that pair of random variables is the same as the previous pair of random variables. That's all I'm saying. That is, you pick R first according to E, then UI RE. That is just speaking UI and R according to the event E. I'm saying that that's the same thing as almost the same thing as picking R from E, ignoring the fact that E has happened, and then picking UI from R. And here I want to say almost the same thing. Then I'm going to pick up. So let's don't mess this up. I'm going to pick up first RC from E, and then UI from RC and E. So that's just picking up UI, RC, all of them according to the event E. And I want to say this is the same as I first pick RC from E, and then I ignore UI. I ignore C and E. So this I claim would just this random choice. This will be just root D plus H by N. Right. And that's just because the event now is not, the previous event has got replaced with the event E and C equals C. But this is an averaging over C equals C. Therefore, you would get there will be a convexity. If it was the reverse C equals C, then clearly D plus H. This exactly, but this is sort of an averaging over the C. You will need one convexity and you will get exactly this. So this is one more level of convexity over the previous. And this is the lemma which we will be using. So we are going to sort of be doing this sort of thing. We're going to pick a random variable. We will use this lemma to say that certain things will be true even if I drop some events.
That's why you need C to be bounded.
I need the support of C to be
So
bounded.
you're essentially just going to ignore that, like count that as error.
Okay. Good. No? Now back to this. And what are we going to prove? We're going to prove exactly this statement. What I want to prove, back to proof of, what did we have to prove? Xi, yi, conditioned on WS. Substitute, drop that. This is what we wanted to do. Xi, yi. RC, WS, and Xi is the same as Xi, yi. RC, WS, Xi, and yi, and a similar event for this is what we want to do. Yeah. So recall what R was, what C was. This one C was the set of answers to both the it's just the answers limited to the coordinates in S. That is, so the proof was generated all the answers based on, but you are limiting it, you are only leaving out the answers to coordinates S. That was C. R was the questions, but not all the questions. For the coordinates in S, you say R included all the questions. For the other coordinates, you included a random question. There was a random variable V which told you which of the questions you are picking up, and T said correspondingly this. So let's actually do this. So,
And somehow last time, the overview of the proof, you mentioned that we are going to think of S as being small-ish. Right?
you will see that in the thing, but basically what's going to happen is S is not small, S is not all the way up to K. That's all I would want. S is there's a gap. And that actually is not something we will see. That is just the artifact of the statement that we proved. From here to that proof, it will already go. It's basically because this is what we will prove. And we'll be dividing it by K minus mod S. Those are the expectation coordinates. Now, if S was almost everything, this is not going to kill this number here. So I want S to be only a linear, at most a some constant fraction of K.
Support of C will also be largely replaced.
Huh?
The support of C will also be largely replaced.
Support of C would also be large. Yes, support of C will also be large. So that's the reason. So it's not going to come in the phrase proof. It's already from this lemma to the theorem is where that clear proof. Because all the n's in the proposition are going to be replaced by K minus mod S. The expectation is going to be over the coordinates not in S. So C was this, and R was XY restricted to S, and VT restricted to S complement. Now it will be convenient for me. T is the coordinates which I have picked up according to V. Let's call T bar to be the other coordinates. So recall Ti is set to Xi if Vi is 0, and yi, if vi is 1, it will be convenient for me just for notation to keep ti bar to be exactly the opposite. The ti bar is what Alice and Bob have to generate. The x part of ti bar is what Alice has to generate. The y part of t bar is what Bob has to generate. Now what I want to do is apply the last proposition to some of this proposition. So this is the proposition we mostly be working with. We'll apply one double bar. But you get what did proposition say? It said RC conditional, this RC, and then we're going to apply for a different RC conditionally, UI conditional RCE is the same as this object. What we will do it with apply proposition 2 with E being equal to WS. E is the event WS. C is going to be the event C itself, what we had. R is going, and I believe R is also going to be R equals R. And UI will apply the event TI bar. Okay. So we get first I pick RC condition to WS. T bar conditioned on just R. I'm ignoring the fact that C has been picked up, WS has been picked up. I want to say this is close to RC conditioned on WS and T bar with everything else, or WS and C. And this is expectation over I not in S. There's some, so it's actually I'm going to do it just for this is only going, so it's only going to happen for one coordinate. It's TI bar, the ith coordinate. That's the ith coordinate is where I'm in this differentiation. The expectation I not in S, and it's going to be some quantity delta I. What will delta I? Sorry, it's just going to be delta. What will delta be? Delta, an upper bound for delta, we pure into square root of d plus h by n. So this is going to be square root of, by n is going to be 1 minus k minus mod s. D is 1 over probability WS. H, see, it's one of the values of the answers. That is basically size of S cross sigma 1, sigma 2. Actually, it is log sigma 1 plus log sigma 2. H, it's not 2 per H. That's so delta. Let's fix it to this quantity throughout. Okay, so let's keep delta in mind. So all our errors will be at most delta at various points of time. Okay. Now let's clear that inequality. The right hand side is a complicated thing. The left hand side, pi bar r. Now pi bar r there is no, I haven't revealed the answers or whether you have one on these coordinates, yes. Therefore, it is independent across the coordinates at this point. Or though it has information about all the k coordinates, they are basically independent, and therefore Ti bar r should only depend on. So I want to say that you're going to have this. So we get the following. So right hand side, I'll copy it as it is. Let's write it this way: RCWS Ti bar RWSC. This is what I had. This we have said delta I naught in S is RCWS Ti bar R. But this is identical to RCWS just Ti bar Vi Ti. It doesn't depend on the other coordinates at all. Okay. But let's stare a little more. What is Vi Ti? Vi Ti is just Vi is completely random variable. And this is with probability half Yi conditioned on Xi or Xi conditioned on Yi. Now I want to clear because of that. Let's condition on the random variable Vi is 0 and just write this statement. When I condition on the random variable V, what happens when Vi is 0? When Vi is 0, this becomes a random variable Yi. Ti bar becomes a random variable Yi. That happens exactly half the time. And when I condition on the random variable Vi is 0, this inequality, this approximation should be true with at most 2 delta. The error can be at most 2 delta, because if it's more than 2 delta, this is an event that happens with probability half. So condition fix Vi equals 0 occurs with probability half. In which case Pi bar equals Yi and Ti equals Xi. So I want to just go to the particular event Vi is 0 and write the whole thing above. So we'll get that. Hence RCWS. This is Yi conditioned on RWSC is delta I naught in S, 2 delta RCWS Yi conditioned on X.
Now the condition found Vi in the condition relation to Vi equals to 0.
Where should the
In the left hand side.
In the left hand side, I claim it's not needed, because if Vi is not 0, Yi is here already. You can just pull it out. I'm just because of the way we have constructed it. Otherwise, I'll have what you say is true. I have to condition on Vi being 0. But the fact is, when Vi is not 0, you have the correct distribution for Yi, because that's already here, there, and here. Yeah. Okay. Now we have all the things. We're going to do a bunch of this jugglery of moving random variables. So are we done?
It's also similar to RC's conditional after this Xi dot Y.
Yeah, we have the other one. So I will just do one of them and be done in the whole thing. So let's find the argument. So we had there is Xi Yi being picked globally from the correct product distribution CR minus I so R minus I, by R minus I mean R minus this whatever is on the VI/TI coordinate.
And shouldn't it be exchange over the condition of W?
Huh?
Shouldn't-
These will notice that these both are more or less the same, whether I put X or Y. Yeah, so the event which I'm looking at is you're given the game starts with you getting this, and this is the view of, and then this is what the party which knows both the variables is going to generate. Now, I want to say the same, almost an identical copy can be got by a guy who just knows one of them. So we're going to do the various steps. The first step will be this is at most delta I naught in S, Xi, Yi conditioned on Ws, Cr minus I, Xi, Yi, Ws. This actually is a smaller delta. If there was not that variable, but I'm going to just throw that in. This one did not require K log sigma 1, sigma 2. Now this is identical to, so this is identical to, what is this? This is X. This is just Xi, Yi, Cr minus I, Ws. That's perfect. That's exactly how that's being generated. Now, let's write this as Yi, Cr minus I generate that according to Ws, and then this is where I'm going to apply this object.
The exchange condition.
Sorry. Xi conditioned on what should I do? Ws on this is exact. This is from what we have above. This is exactly 2 delta I naught in S Yi Cr minus I Ws Xi conditioned on just Yi.
There's a wire in the line above. Xi condition on WL, CR, and
Yeah, that one, no? Yeah. So basically, this dropping is what we got from above. But then we are done. So now I will once again write this in a slightly different fashion. So this can be talked about as I first pick Yi conditioned on Ws, and then Cr inverse Yi and Ws and Xi Yi. So this is actually equality. And then this we know this is once again I naught in S 2 delta. This is like Yi Cr minus I Ws Xi conditioned on Yi.
Just give them.
But that's exactly what we want. It was Xi Yi Cr minus I Yi and Ws. So this is stating that Bob, from Bob's point of view, what he gets is exactly what the party who knows both the variables samples. And the same argument for Alice. Therefore, the three copies of CR which they have are all very close distribution. So they will use Olympian correlation sampling to get an identical copy and then finish it. That's the end of it. Please. Equality. Okay. Okay, that known as parallel rotation. And there are various. What have we shown? We have shown given Hollenstein's proof of parallel rotation theorem, stating that if you repeat a two-prover game k times, the value does go down exponentially. Since then, there have been several work on parallel repetition theorem. What are so immediately after Hollenstein, Anup Rao observed this, and Anup Rao showed that in this whole proof, if you further notice that if it's a projection game, that is the answers projection game, once you know the answer to the bigger prover, you know what are the answers to the smaller prover. So you don't have to condition on both A and B. Then you actually notice that you don't have to give out the answers. In this whole argument, the answers need not be given. Therefore, the proof doesn't deteriorate with the size of the answers. Right now, the proof seems to deteriorate because of this to power h. The quality of the decay is affected by this, and Verbitsky has an example which shows that actually it will get this one. If it's a projection game, Rao's this one just carries this large enough and realizes that actually you don't have to carry them.
The support of C will be small.
Not support of C won't be small. It will still, the fact is, it's not that log sigma 1, log sigma 2 that's the issue. It's that S which is going to cause the major issue over here. And what Rao says is actually that's not even that, it's not, in fact, there is no such expression. You can show with high probability you are going to go into an event which so he will modify this argument a little bit. You have to look at Rao's paper and say that with high probability, you can assume the answers are of constant size. You forget about the growing size in this one. Managers will do this. In the case of projection games, this is Rao's contribution. What are then even subsequent after this? Denur and Stoyer then gave a completely different proof. They didn't. This is a proof based on information theory, basically relative entropy all over the place. They gave a more analytic proof using Cheeger's inequality of the same this one, but their proof had an advantage to it. Basically, the main advantage was it was more powerful than this. Right now, this proof says that the value of the game is 1 minus epsilon. If you repeat it, this goes like 1 minus epsilon square to something in k. So, but suppose the value of this 1 minus epsilon was actually some number very close to 0. It's now that fact you're replacing 1 minus epsilon by 1 minus epsilon square and then doing it. That fact will be completely lost. That is, you started off with a game which already had low value to begin with. So they give a more nuanced analysis in the other world, in the different proof in the analytic world, which shows that small games also observe parallel repetition. And this was important for reasons we'll come to later on in the course. That is, small games also observe parallel repetition. They also go down exponentially. So if the original value was some delta, 1 minus epsilon delta, what they will show is this is go more something like square root delta to the power, something to this fact they will show that it goes square. So this is what they show. But they managed to show this only for projection games, not for all games. Then Braverman and Garg went back to prove the same statement with Denur and Stoyer proved but using the information theory, using the techniques we saw now. And they showed you could get exactly what Denur Stoyer proved. But not only that, they could answer all games, not just projection games. So that's the state of affairs for parallel repetition. So what I will do now is in the next 5 minutes we will summarize what we have, the two-prover label power game, break for 10 minutes, and then come back to see it's an application to. So what do we have? So we had the PCP theorem. So where are we? The PCP theorem, one way of stating the PCP theorem is there exists a constant epsilon 0 between 0 and 1. This constant is something like 0.999 or something. And sigma 1 and sigma 2 constant size alphabets. Such that, yeah, 1 minus epsilon label cover, which answer side is NP hard under poly time reductions. This is, we saw that PCP theorem can be stated in this two query.
So because when you reduce the k query to what to 2 query.
Yeah, because of that. So there are some constants that, this epsilon is like 0.99999. The alphabet is the alphabet is possibly three or something, 3 and this one. Anyway, we had this statement. Now, if you apply passive repetition to this, about, what we get is this PCP theorem plus passive repetition. What's basically going to happen? We are going to be able to, the gap 1 versus 1 minus epsilon is basically going to go down to delta, which so basically we're going to get the following for all delta in 0, 1. There exists alphabets sigma 1 and sigma 2, and furthermore size of sigma I is going to be, how much will the size of sigma I be? So original bit complexity was constant. We are applying k parallel operation, so k times this one, but that is the log of this one. Therefore, this will be actually poly 1 over. The number of symbols will be poly 1. When I talk about one, it will be poly 1 over delta. Such that gap 1 delta LC sigma 1 sigma 2 is NP hard under, what's the running time of reduction? It's poly, it's first is polynomial, first to get to that, and now we have to repeat the game k times. So the instance size goes from n to n to the power k.
But for constant delta.
For constant delta. So let's, because I'm rating it for all delta, let's state it a little under n to the power order log 1 over delta time reduction. Okay. So this will tell you for all constant delta you do get this, but once you go to super constant, this is not a polynomial time reduction. That's the reason why I'm writing it this way. And furthermore, this game was actually this label cover was a projective label cover. And parallel repetition will maintain projectivity. So this is also, and furthermore, and even when restricted to projective instances. And this will be important for us in the next part. And the same thing is true.
Unique games means it's projective with respect to
Both directions. What I thought I finished in half an hour and way off estimate. But this green thing will be the starting point. We just assume this as a black box and do the second part. So let's break now. Break now. But we'll take a shortish break, not a. So should we meet at 11:15? 11:15. Let's pause now. Okay. Let's continue. So go to part 2 of today's lecture, which we'll be considering. We'll be proving optimal hardness of max 3 len 2. Okay, what is max 3 len 2? So the instance is given by n variables x1, x2, xn and m linear equations, and each linear equation is of the form xi1 xor xi2 xor xi3 equals pi. So the 3 comes from the fact that each linear equation involves 3 variables, and 2 comes from the fact that these variables all come from GFT. So the n such equation and the goal is to find an assignment, find a Boolean assignment that satisfies as many equations as possible. That's max 3 len 2. So be convenient for us to come up with a gap CS len 2 problem. So the S instance in here C is 0 is half is less than or equal to S, is less than C, is less than 1. And you'll see why I'm giving these numbers. Usually 0 is less than or equal to S, less than C, less than or equal to 1. But I made S to be at least a half and C to be strictly away from 1. And you'll see it in a reason why I'm doing it. So the S instances are instances phi.
Because half of protection can always be.
It's because half can always be satisfied. And 1, if it is 1 that say if it's half can always be satisfied, 1, if it is 1, that's also easy to check. Therefore, you're going to instances phi such that at least C fraction of constraints can be satisfied. And no is instances phi that at most yes fraction of constraints can be satisfied. If C is equal to 1, this problem becomes easy. If S is equal to half, again the problem is easy. If S equals half, there is no instance. So when I mean at most, I should probably make it less than. There are no instances if S is equal to half. So no, I made it less than equal to, it's fine. The way it is actually. If S is half or below, there are no instances. If C is 1, it's easy to check if something is a 1 instance. Therefore, this is the interesting case. And the theorem is one of the several optimal results of the cluster, where he shows basically that's the best you can do. Because for all epsilon and delta constants in 0, 1, gap 1 minus epsilon half plus delta 3 and 2 is integral. Which basically says, given a set of this ones, it's going to be extremely hard for you to come up with an assignment that satisfies more than half. More than half plus delta. Half is easy. Anything better than that is going to be very, very hard. Basically. So this is going to be an honest to God reduction. We are going to reduce from SAT. That's anti-hard. So the reduction will go of the following type.
This has something to do with parallelography. This has something to do with parallelography.
We will use the final label cover version which we proved using him. This reduction will be from SAT, but then it will go via first gap 1 mu label cover and gap basically we will show for all epsilon delta there exists a mu such that the reduction holds. So I want to get some gap 1 over epsilon 1 minus epsilon delta. To get this 1 minus epsilon delta, there will be a label cover with a particular soundness mu that I want. So this result will prove it for all constant epsilons and deltas.
Is label covered with binary alphabet?
No. So this alphabet. So to get 1 mu, I have to get. I have to do parallel. Well, it will be the corresponding alphabet given by parallel.
And at the end, you will gap 1 minus epsilon half plus delta.
Sorry, half percent. That's going to be the nature of our. Okay, we're going to do this reduction. We're going to do a usual type reduction. So the first reduction is this reduction is what we saw, what we have seen over the last 7 lectures. This is PCP theorem plus parallel repetition. This is what's going to be going to see today. Okay. It's the second reduction, so there will be composition of 1.
When talking about the label cover instance, I would say
so it will be a parameter. It will be a parameter. It's the parameter will be the gap 1. When I say 1 mu label cover, I mean label cover in which the alphabets are allowed to be poly 1 over mu of size. It will play a role. It will play a role for us. It will play a role. The running time of that reduction, it will play. Certainly, that R2 reduction will run. Certainly, the total reduction, it will not fall on under poly time. It will be certainly under n to the power log 1 over mu. And there might be a further R2 might have involved some more functions of mu, but okay. Right now, for this pointer, I'm going to keep epsilon delta as constants. You give me an epsilon delta, how close you want to get, I will give you a mu, so everything will be a constant because of this. Now, how do we go about doing this? So what do we have? We have, this is our label cover problem. U, V, and then there's a pi E. And what do we know if I give this? I'm asking if there's a coloring, that is, can I put a color here and a color here? In fact, I have color for each one of these guys. Let me make these smaller to show that this is a projective output. Such that every edge is satisfied. The label cover says, is there a coloring to the left hand side and the right hand side, such that, can you distinguish, is there a coloring such that everything is satisfied or at most a mu fraction of it are satisfied? And we know that this is NP hard to do. We want to now convert this into a max 3 len 2 instance. This is a coloring problem now. I want to convert it to max 3 len 2.
Sorry, the colors come from sigma, right?
The colors are coming from, this is coming from, here the colors are all coming from sigma 1, and here the colors are coming from sigma 2, and these are projected constraints.
When you say they are satisfied, that means the predicate is.
So the constraint is basically of the form pi e is sigma 1 to sigma 2. You just pick every edge and see if pi e of the left alphabet is equal to the what's written on the right hand. Okay. So it's a projective constraint of this type. Okay. And from this, I want to now cook up a max 3 len 2 instance. I want to do further reduction to get a max 3 len 2 instance. What's one way of doing it typically? Most reductions which we work are very gadgety. That is, they locally go and change. At least all the NP completeness reductions which we saw, which we have seen in the first complexity course, will all be there. The PCP theorem is not like that. PCP theorem does this low degree extension. It just arithmetic. It takes the whole proof and moves around. It's not what is called a gadget reduction. The gadget reduction is take each part of the statement and modify it locally. I'm not formally defining this, but it should be clear that the NP completeness reduction which we saw in the beginning, in the introduction course to complexity, is very different from the PCP reduction. PCP reduction looks at the whole object, does a whole lot of massaging to it to get the final label cover. Whereas the reduction from SAT to vertex cover, a SAT to independent set, they're all very, very local reductions. We will now, actually, this reduction will be a local reduction. Reduction to label cover involves the whole PCP theorem, but from there onwards, what we'll now do is actually be a gadgety reduction. In that sense, what do you want to do? So every vertex, so the proof is going to be the set of colors. Now, instead of the set of colors, what we'll expect is give me an encoding of the colors. We'll expect as proof list of colors, list of the colors. Instead of that, we'll expect some encoding. Under a suitable, we have to decide what encoding we want to do. So each color is going to be encoded by a larger object like this. So instead of this one, so a different color for this is going to be the proof of each guy. Instead of giving this color, you're going to give an encoding of this color. And this encoding should be over the Boolean alphabet, because eventually it need not be a bit each, but it would be a string of bits. So for every this one, we are going to expect to give an encoding of what the actual color should be. And this encoding should do, and now the only constraints we can check. So this is a sequence of bits I give here, a sequence of bits I give here. The only constraints I can check is pick 3 bits and check their XOR is some value. Those are the only because I have to output a 3-lin instance. Those are the only constraints I can output. So, and these constraints must in them do multiple things. Firstly, they must check that these are actually valid encodings. And further, then they should check the valid encodings of colorings which satisfy the label cover problem. So there are multiple things. We want the encoding. So they haven't told you what the encoding is, but the encoding, if you want to construct the simple, this is the obvious thing we would want to do. Come up with an encoding. I'm going to very much use the fact as a projective. You will see that in the proof. It will pop out in the proof.
And by projective, you mean you just mean the unique.
For every left-hand side, the constraints are exactly of that form. Pi e going from
functions from pi to pi sigma 1
to sigma 2. For every edge, there's a function from sigma 1 to sigma 2. That's what I will be using.
So in this particular case, sigma 1 means it's a response to the key queries given to the prover, and sigma 2 is the actual proof string.
No, so in the it's firstly, so k you're using k, but sigma 1 is the Q queries to the prover, sigma 2 is the actual proof, and then it's been repeated k times by parallel repetition. So sigma 1 is actually not Q provers, but a k tuple of Q provers, and this is k locations in the proof is what I'm asking.
And here for this specific case, function pi is literally a projection on a subset of coordinates.
It's literally it's a projection in the geometric sense of this one. I don't care. I just use the fact it's a function. As a form, it's a function. This. That is the pi is usually a relation on sigma 1 to sigma 2. It just says which are the valid subsets. Here I'm saying the relation given by a function from sigma 1 to sigma.
No, I mean the fact that it's a projection. Now it feels like, I mean, I can imagine a linear constraint capturing this whole situation, because so suppose that sigma 1, this function pi is just going to project sigma 1 to some subset S of coordinates.
Yeah.
So then another way of thinking of this projection is that we add the vector corresponding to sigma 1 to a vector which equals sigma 1 on S complement.
Okay.
Such that when we add these two guys, all that's the zero everywhere else, and all that survives is.
Yeah. So the think about it, the projection is easy. The what is hard to check is so let's look at it. Let's assume that we had 3 SAT. We had 3 SAT. So how was the label? So the Q queries versus 1 query. Let's think it was 3 SAT, 1 versus 0.99. That was this one. So the left-hand side are basically clauses, k sets of k clauses. The right-hand side is set of k variables. The left-hand side assignment is satisfying assignment to the k clauses. The right-hand side assignment is just a Boolean string of length k. Now, what you say, if I had given satisfying assignments is 0, 1 to the 3 to the power n, then it's literally a projection. But then I have to make the one nonlinear constraint that actually that is a satisfying assignment. Or I just represent it as a symbol from, I use just an alphabet of size 7 to the power k to tell which of the guys it is. And this is an alphabet of size 2 to the power k. And this is just, it's just a projection. So I could do one of the two things, but in either of them, there is a nonlinear aspect to it. In one aspect, I have to check that the alphabet given to the left-hand side, 0, 1 cube is actually a satisfying assignment to the k clauses. So it's not fully linear is all I'm trying to say. It cannot be fully linear because if everything were linear, the system would have been trivial to solve. Gaussian elimination would have solved it. All the set of constraints on the whole object cannot be all linear. They have to be nonlinear constraints. And you can capture it in several ways. Right now, I'm not going to assume anything about it except for the nature of projection. Later on, as for certain specific problems, sometimes this linearity might help us. Right now, I'm not going to focus. Okay. And what do we want of this encoding? This encoding must be testable. Firstly, using only a tuple of 3 queries. And predicates of the form X or Y or you query the 3 queries and just decide those 3 queries, do they XOR to this bit? That's so far we never talked about how to constrain the predicate. We are allowed an arbitrary predicate, but now I further say you are allowed to query 3 and do this. And in the process, you need to do 2 things. You need to first check it's what do I find the objects? I had to do a code word test. In these 3 queries, that is check it's a valid encoding.
The code has to be globally tested.
Yeah. All tests are of the previous type. Those tests and the tests are all of the type, and using such test types, I must be able to check firstly it's a valid code word test, and then furthermore, it's a consistency test. That is, whatever it is encoding satisfies the check it's an encoding of a coloring that satisfies the label car predicatives, label car projective predicatives. Okay. And actually, carrying sigma 1, sigma 2 might help me to. I'm going to make it L and R, the left hand alphabet and the right hand alphabet. L is the left hand side. Alphabet. And R is the so this projective constraint is actually going from L to. So we need to first come up with an encoding which has all these features. So what is the good encoding? We have seen several codes. We have used a few codes over here. We have seen one question about encoding.
Only code which can be queried with 3 queries and locally tested.
It's Hadamard code, but Hadamard code has very linear property. I need to check some non-linear.
Quantitative condition.
We did something like that, but it didn't get. You are only allowed to query 3 queries. So what we do is we'll do the other extreme. So we'll come up with let's use right now. Notice I don't care about how wasteful the encoding is because the colors are constant size. L and R are constant size. So the encoding can be as bad as possible, rate wise, as long as it has these features. Because the rate could be exponential, doubly inverse exponential, inverse doubly exponential. I don't care. If you do that, then what is the worst possible code you could give? Worst possible code is what's a code? A code is you can encode a k-bit string using some n-bit string. Now everything in the n-bit string should be a function of the k-bit string. Otherwise, there's no point giving that. So it should be a function. Now, question is what's an encoding you can give? Let me give. There are how many functions on k-bits? 2 per k. Give n for every such location. For every function, give me that So we'll do a code which is the worst possible coding, because I want tests which have such nice properties over here. So to get these nice properties, we'll come up with a coding which has every possible function, so that then I can do the test. So what we will do is we'll call what is a code, that question which we're going to ask is what is a code that supports these properties. The answer, which due to Bellare, Goldreich, so then is use the most wasteful code. Which we call the long code, because it's the longest possible. Among all codes, it's the longest possible code you can come up. Any other code either repeats a bit the same multiple times, or has a bit which is irrelevant to the input. So we'll call this aka the long code. So it's the long code from L. So it's going to map every string in L. This is a log L bit string to a string of length 2 to the 2 to the L. So 2 to the 2 to the log L, which is what? 2 to the 2 to the log L, that is 2 power L. And we will think of these as each one of this as a function on the space. So basically, what is it going to do? It's going to map think of 2 power L as an index to the set of Boolean functions f going from L to 0. So let's call this. Let's call the set Fl. So write long code L to 0, 1 FL. What does that basically map? I'm going to map a string A to f of A. F. Okay. Every code that we think of is just picking a subset of functions in FL and doing it. The Hadamard code is picking all linear functions. This is not the Hadamard code is such a code in which you are working with all linear functions of the input. Here you're working not just with all, so that's exponential. This is you're working with all functions, so it's doubly exponential. The blow up is inverse double exponential. Let's see if this code has the property. The point is we want such where is this property? So what's the code to work with? BGS suggested actually use the long code, and they came up with some analysis, but not the optimal analysis. And Johann Hastad then subsequently gave a Fourier theoretic based analysis to analyze the long code on this object. So we need to recall, we need to do two things. We need to first test. If, so I'm going to give you a 2 power L long string. I need to check it's a valid long code. Firstly, one needs to do that test, and then one needs to test that it's a valid long code encoding of two colors which satisfies the projective constraint. Let's ignore this latter, the second one. Let's just do the formal. Can I come up with a 3-query test that, given a 2 power L long string, checks if it is a valid long code encoding? It's a valid long code word.
Error testing.
So let's check with the VLR testing. So I want to actually make the question now is, code word test. This is sometimes also called, so what we're going to do, what we're going to now do is what's called the long code test. Sometimes this is also called a dictator test. And the reason for that is basically the following object. So what am I given now? I'm given a function. I should have possibly indexed this as. Okay, that is fine. So suppose now I'm given a string W in 01 FL. We need to check the string. So let's think of what do I want to check with this object. Yeah, so this string I'm going to view it as W from FL to 01. Obviously, I can view the string as this way, and I want to check that it is a long code test. That this is actually, so for every function in the Boolean space, it's giving you a bit. For every function, it's giving you a bit. What we want to check is actually the bit it's giving you is the evaluation of all these functions for the same location. There is one underlying location. So what is it? W is a valid code. So W is a valid. W is a valid long code word. If there exists an A in L such that W of F is equal to F of A for all F in. This is the just definition of it.
Each element in FL is now an L-bit string. Each element in FL is now considered as an L-bit string.
Sorry, this is changed. Capital. Why is it an L-bit string?
For each element in L, you are saying that or not.
No. Each element in what?
For each element in L, you are saying whether or not it is 0 or 1.
Not for each. So I give you a W, which is just a long string, which is a string in 01 to the FL, and I'm asking you, is this a long code word?
This is like a linearity test.
It's almost like a linearity test. Let me just defer that. Before that, I want to say why this is also called dictator test, and I will say why it is called a dictator test, and then I'll come to the testing part of it. So what do we need? So I give you a W, which is basically a string in 01 to the FL. I could give you any string, But that string I'm going to interpret it as a function from FL to 0, 1.
So this
Mhm.
is it now continuing to think of W
Yeah.
as a function from 0, 1 power L to 0, 1.
It's not 0, 1 to the power, it's 0, 1 to the power 2 to the L, no? 2. So W is so FL is the list of all functions on the set L. So FL itself is of the size 2 power L. Therefore, FL, this is 0, 1 to the power 2 power L to 0, 1. You can think of it as 0, 1 to the power 2 power L.
No, FL has size 2 power L.
FL is size 2 power L.
It can be thought of in direction with 0, 1 power L.
Yes.
So W is continuing to think W.
W is a function from 0, 1 to the L. Yeah. So, okay. So if you do it that way, so once again, how do you want to? But this is, so in that language, this is.
In that language, it's clear where it's a dictator.
Yes. So 0, 1 to the L to 0, 1. So each of 0, 1 to the L inputs gives a function, the truth table of a function. This is just picking the A coordinate in it and outputting it. So it is just stating that W of any string F is FA in this language, or in this language, W of any string X is exactly X at A. So it is a dictator corresponding to A.
What is it? Dictator?
Dictator is you have a n-bit string and a function of it. The function disregards all the other bits. It just answers according to a particular bit. A dictator is a function, or equivalently, gives a long code word. Yes. That exists A in N such that this happens. No, but this is exactly, but these are also called. Also called dictators. Dictator is just a function from 0, 1 to L to 0, 1 in which you just pick, you ignore all the L coordinates, you work according to just one coordinate, and that's what this is stating. There is no W the function in L bits. W of X is just X to the A. So these are alternately called long code tests or dictator tests, depending on whether you use this as W01L to 01 or WFL to 01, whichever. And we will use these names.
So now Arrow's theorem.
Huh?
Arrow's theorem.
Arrow's theorem will work for what?
And first to BLR, Arrow's theorem. So first to BLR will check it is linear, and then if it's linear, Arrow's theorem will say ideas for it given that satisfy this.
We're going to put all of that together. Arrow's theorem is more than what we want. Dictator corresponding to. Yeah. So you're given a string W of the form 01L to 01. I want to check if it is a long code. Basically, it's a dictator. You can run the BLR test on it. Certainly, BLR test will pass with probability 1 because the function Wx going to XA is a linear function. But not just dictators will pass, all linear functions will pass the test with probability 1. That is, things of the form XA plus XB, XA plus XB plus XC, all of them will also pass the test with probability 1. Somehow you want to modify the BLR test such that if the test if any linear function which has arity larger than 1 passes it, as for linear functions with large arity will pass the test with smaller and smaller probability. You want to change modify the BLR test. So the BLR test certainly is a test which all long codes will pass perfectly. But all linear functions will also pass perfectly. And you don't want that to happen. You want only long codes to pass it very well. So what we'll do is we'll modify the test slightly such that all linear functions will pass, but the probability will be the larger the support of the linear function, the smaller the probability with which it will pass. So let's do this. So this is what Hastad suggested. So we will define what's called the epsilon perturbed linearity test. So the observation is the BLR linearity test. So all dictators satisfy BLR test, but so do all linear functions. So modify BLR test so that the probability of accepting linear functions with large support is small. Fair enough. So we will define what's called the epsilon perturbed BLR test. This has access.
So what sort of quantitative redundancy do you have in mind?
It's small.
Is it like 1 over? the
So-
width, or is it, is it 1 over the width?
Is the what I will have will be 1 over the width.
It seems like you, so in BLR, instead of taking X and Y.
You're putting x, y, and x plus y over there.
So here, maybe I want to pick X and then pick a random index that get Y. So work with this X plus Y and not take.
You're saying I'll take x and x plus ei. X and x plus ei.
On the arrows theorem test,
What is the Arrows theorem test?
so you select the predicate x, y, z, which are not all equal. And everything, x, y, c.
Are not all equal, but that's not the sort of test we can afford to do. Because
You are only linear.
we are only allowed to do linearity test. So what I will do.
Is there two little random?
Here,
The thing.
there is too little randomness in that. So we will consider such a test when we do max cut. And we don't know how to prove this, so that's where the UGC will come into picture. We don't have enough.
Seems like a natural.
It's a natural test to do. We'll flip this one, but we'll do something along this lines. This one. So f is what I've been calling W so far. F is this function from 0, 1, L.
So why can we afford to only linear test?
The max 3, you remember the predicate which we wanted to. This is the properties we wanted.
You want to reduce it to max scale then.
So the only test which we are allowed is query 3 queries and tests of the form X0. So that's what we will do. And within that set of tests, we must both be able to check it's a code word as well as consistency. So F is what I call W now. So just go back to the BLR notation. So we'll do the same thing. We will pick X and Y at random from 0, 1 to the L. That's all was BLR. Now we're going to pick. There's going to be a noise parameter, which will. There's already epsilon. So pick an eta in 0, 1 to the L as follows. Eta to the A is 0 with probability 1 minus epsilon. It's 1 with probability. So eta is just it has with mostly it is zeros, but epsilon fraction of the time it is 1, and you do this independently for all the L coordinates. Previously, we were setting z to be equal to x plus y, but we set it to be x plus y plus eta. Then accept if f of x plus f of y plus f of z is c. That should be a LR test. Epsilon perturbed LR test. Notice what's going to happen. Let's try to analyze the what happens to dictators. What is the probability in which dictators are passed?
1 minus 6.
1 minus epsilon. It's the probability that that particular coordinate you flip. So that's the completeness of this test. So completeness. If F is a dictator, that is, there exists an A in L, so that f of x is xa, then probability, the random choice of x, y, and eta, epsilon perturbed BLRF accepts is exactly equal to 1 minus epsilon. Okay. Now I want to analyze the soundness of this test. Now, as in the BLR case, it will be convenient for me to work with the plus minus 1 word. So we'll assume that f is not a function. So it will be convenient. Soundness analysis. Instead of 0, 1. So the domain will think of still as 0, 1 to the L. The range, instead of thinking it of 0, 1, we'll think it as plus minus 1, in which instead of giving b, we'll only give minus 1 to the power b. Okay. So think of f that is f as a function from 0, 1 L to plus minus 1. So what's the probability over x, y, and eta of epsilon perturbed BLRF accepting? This is exactly expected value over x, y, and eta of 1 plus f of x, f of y, of z by 2. Because in the plus minus world, if it's 0, that is 1, so that's the probability which it accepts. Okay. So suppose suppose probability of accept is at least 1 plus rho by 2. What does that mean? That means rho is now let's go to our Fourier analysis. Let's do exactly what we did for this one. So this is expected value over x by eta summation alpha beta gamma f hat alpha. What was the Fourier coefficient? Did I do it in alpha or how did I do it in BLR?
What do you mean?
So did I use
Yeah, you use as a alpha. Effects.
if I index it with alphas or did I index it with sets? Yes.
Now you
Alpha.
like alpha. Yeah.
Fair enough. Into the same thing. So F hat alpha, F hat beta, F hat gamma, chi alpha of x, chi beta of y, chi gamma of z. So z I'm going to now write it as x plus y plus theta. So this is the linearity of expectation will let me take out alpha beta gamma, f hat alpha, f hat beta, f hat gamma outside. I can write chi gamma of x plus y plus theta as chi gamma of x times chi gamma of y into chi gamma of theta. And then chi gamma of alpha x and chi gamma of x together can reduce chi of alpha plus gamma of x. So
So
this
these things we are working the plus minus one will be x, y.
I'm assuming the domain is 0, 1 to the L, the range is plus minus. It depends. If you want to do it, then make that also product. It's up to us how. So this is chi of alpha plus gamma of x. Y of chi of beta plus gamma of y. Chi gamma of beta. Is that okay? So now this quantity, so just because x, y, eta were independent, I could break this expectation into 3 parts. So I've done 2 things over here, done multiple steps over here. Chi x of alpha plus gamma of x is 0 unless alpha equals gamma. Similarly, chi beta plus gamma of expectation of y of this is 0 unless beta is equal to gamma. Therefore, we get that alpha, beta, gamma should all be the same. So this is just you have 1, you have f hat alpha cubed. These two will disappear. Those two in that case is 1 and 1. So all you have is this one. Expected value of eta by gamma of eta by pi alpha. Is that okay?
So the expected value vanishes unless alpha beta gamma are the same. That's what you do.
Yeah. And then I'll just rewritten that expression.
Plug it.
I plugged it, yeah. And now let's write down what. Because what is this? This is, let's find out what this is. Expected value of eta. What is chi alpha? Chi, this is just minus 1 to the power summation alpha I eta I. Which eta is a product distribution across the coordinates. Therefore, that this thing actually this nicely breaks. So first I can write this as expectation over eta, product over I, minus 1 to the power alpha I eta I. Eta is product across the coordinates, therefore I can take the expectation of the product as a product of expectations. So I have pi I What is this quantity? Huh? No. So eta I is 0 with probability 1 minus epsilon. So whenever it is 0, so whenever it is 0, so it's 0 with 1 minus probability. So there's going to be this quantity is going to be 1 with probability 1 minus epsilon. Notice, firstly, if alpha is 0, this is always 1. If alpha is 0, this is always 1. Now let's go to the case that alpha is not 0. Alpha is 1. So I'm going to write this slightly separately as firstly write this pi of I such that alpha I is 1. Then this is just expectation over eta I minus 1 to the power eta I. Okay. What is this quantity? It's not epsilon. It is
minus 2 epsilon.
1 minus 2 epsilon. 1 minus 2 epsilon. Therefore, this is product over I. Alpha I equals 1. 1 minus 2 epsilon. In some sense, it's 1 minus 2 epsilon. Right, alpha. Great. Then going back to the thing which we had rho is less than or equal to summation over alpha f hat alpha cubed that's what we have. I'm going to write this in a plug in back.
So you want to break this up into based on support of alpha.
I can do that, but I'll just going to write it. I'm going to write it as expectation. So the f hat alpha square is a probability distribution because summation f hat alpha square is 1. F is a Boolean function, therefore it satisfies Parseval's inequality. So I can write this as f hat alpha square into f hat alpha into 1 minus this one. Therefore, this is the expectation of alpha when picked according to f hat alpha square of f hat alpha into 1 minus 2 epsilon alpha. So what does it say? So the expectation of this quantity is at least rho. Therefore, certainly there is one alpha. Hence, there exists an alpha such that f hat alpha into 1 minus 2 epsilon by mod alpha is greater than or equal to rho. This particular tells you that this f hat alpha itself should be greater than rho, and alpha can't have too large a support because if it has a large support, this quantity will shrink. In particular,
So we know that the absolute value of f alpha is most 1.
yes.
What was the second comment about?
No, there are two comments. In particular, I want to say f hat, these both are numbers less than or equal to 1. Therefore, this should be greater than rho, this should be greater than rho. That's all I'm going to come to. In particular, f hat alpha is greater than rho. There exists an alpha for which this happens. And this latter thing says size of alpha should be less than order, I think 1 over epsilon log 1 over. Yeah. The formless claim is the following claim. Suppose probability epsilon perturbed DLR F accepts is at least 1 plus rho by 2. It's slightly more than trivial, random. Then I won't be able to say it's a dictator, but I will be able to say that there is firstly a large Fourier coefficient, and furthermore, that Fourier coefficient has small support. That's what I will. So it's like a dictator in that sense. There exists, and then there exists an alpha. There exists an alpha in 0, 1 to the L. Such that one of both conditions are satisfied. Firstly, that on that alpha, it is a large, the corresponding Fourier coefficient is very large. So it's very much focused on that. It's rho large on that. And 2, size of alpha is less than that is support alpha. So this sort of weeds out the larger linear functions. The linear so it does accept the dictator function of reasonable probability with 1 minus epsilon, and the larger the for other linear functions, as their support becomes larger and larger, it's going to accept them with smaller and smaller probability. And furthermore, that's just one, that's the other direction. Soundness says if it ever accepts with reasonable probability, the function should be correlated with a linear function of small support. Of course, one thing this does not rule out, f could have been the forget about dictator, it could have been the constant function. It could have been the constant 1 function, or the constant in the plus minus 1 word, or the constant 0 function. That in fact accepts probability 1. Here, neither the completeness of the soundness claim contradicts this fact. This will come and bite us at some point of time. Just keep this in mind. That is, we have eliminated the large order Fourier, the linear functions of large support. We are ensured dictators are passed with considerable probability. But on the other hand, the constant function 0 or the constant function 1 in the plus minus 1 word is also being accepted. In fact, it's being accepted with even larger probability 1. But at least we beat it out all the other linear functions. That's the completeness and soundness claim. Is this good enough? This is good.
But once you know it's a dictator, then can we have another additional cases of the peak to random concepts?
So we can do all of that, except that already here I've used the fact that test passes with 1 plus rho by 2. We're going to do 2 tests. Typically, that above half will become a 3, 4. You remember we did sort of these multiple tests when we did when we constructed a PCP for circuit start using Hadamard. But there we didn't care about the soundness as long as it was bounded away from 1. So we could do several tests as long as all of them were bounded away from 1. We would get the max of those or some such thing. Here, half is important for us. We need to get half. And so the question was already the code word test itself. You can only get 1 plus rho by 2. Now we need to incorporate the consistency test also into this.
So is relevant for the dictator test? Is relevant for the dictator test, right?
This is what so the dictator test is. So I won't be drawing far. The dictator test has a property. Dictators are accepted with probability 1 minus epsilon. Anything that's accepted with reasonable probability looks like a dictator in this sense. That's all I'm going to. So this is sort of, I'm going to say it looks like a dictator in the sense it is correlated with the linear function of small weight reasonably well. That's all I'm going to get for a dictatorship. I'm not going to delve into more. Like in the proof of arrow theorem, we got much more. This is all I will get, and this will be enough. It's going to be much simpler Alright, we will now plug this in into the Haskell's analysis.
So for example, how do you distinguish between string order from ZI plus ZJ from ZI?
This will get accepted with 1 minus epsilon, that will get accepted with probably 1 minus epsilon square. The hope is those that can distinguish. Right, we'll come to it. And right now, I'm not. So this is just a warm up to Haskell's 3-bit. We'll prove Haskell's 3-bit completely, PCP fully. Okay, this is all I'm claiming is this is a test that is sort of as the linear systems become smaller and larger support, it's accepting them with lesser and lesser probability. It's true that xi and xi plus xj are going to be accepted with very close probability to each other. So the further soundness analysis for the 3-bit PCP will have to deal with all of that. We'll come to that later. Okay. So now let's go back to Haskell's 3-bit PCP. So once again, so what we are now going to expect is Haskell's 3-bit PCP is going to basically do this. So what's suggested by BGS, but we're going to give the Fourier analytic proof of it. We're going to exactly that one. We're going to give this pic to those purple instead of giving the proof will not consist of those blue circles over there. It will consist of purple encodings. In the left hand side will all be long codes or these codes. That will be long codes on the right hand side. That's going to be this, and we're going to make a test on this.
So first we already did the long code test.
Yeah, so, but we're going to merge all the tests together. So Haskell's 3-bit PCPs is the following. The reduction from gap 1 mu label cover to gap 1 minus epsilon half plus delta 3 then 2. What's its input? Its input is a label cover instance. So it's what's a label cover instance? P, which is first a graph, it's set of right vertices, set of left vertices, and edges. It's a bipartite graph. It's 2 alphabets L and R, and then a bunch of projections. So that's the input to this. I'm not going to give it as a reduction, I'll give it as a PCP. So it's now there'll be a proof and it will make queries, and the queries only queries, it will make 3 queries on every randomness, and the predicate will be a XOR of 3 things. So what will it expect as proof? Proof it will expect FU going from 0, 1, L to plus minus, let's go to the plus minus 1, 1 for all U in U, and FB 0, 1, R plus minus 1 for all B in U. What's the PCP going to be? So it's going to, the first step will be take UV at random from the edge. It's going to pick a random edge of the label cover instance. And phi e be the corresponding projection. Now, what we will do. So we are going to do the following. Do the following test.
So the function phi is also there in the encoding.
It's not there in the encoding. The encoding is just encoding the left alphabet, right alphabet. Now I have to tell
I mean, the long code corresponding to the vertex, the color of the vertex. There is a coordinate there that is phi.
not pi e. Pi e is an arbit string. So but pi e can be broken up into arbits.
Or it's not, I see. So for each of the coordinates of phi,
There is a function. So the pi e in out there. So actually let's before we do this, let's look at the picture which we have. Be here to picture. So that's the label cover instance we have. Let's focus on a particular U and V. So there was a previous alphabet, one which has now got blown up. To this largest alphabet. So this was an element of this belong to L, this belong to R, but now this itself is a 0, 1 L long string. This is a 0, 1 R long. No, it's a 2 power N long string for everything. So the length of the string, it's not an element of this. That is the, so I should have possibly said the length of this is 0, 1 to the power N. For every such way, there is a coordinate over there. The ideal way to think of this would be actually not this, but this is the it's the 0, 1 to the L hypercube and it's labeled with bits. It's a labeled hypercube. The same thing over here. The label hypercube. And the label is basically this FU. And this is FP over here.
So I'm thinking of pi as a function from coloring of U to coloring.
So pi is a function.
Labeling of.
Pi is a function from L to R.
And this pi is same for, it is different for different edges.
Yeah, it's different. It depends on the edge. Depends on the edge. Okay. And we are only allowed to query 3 queries. Notice the code word test itself. So we could design multiple. So what BGS, how did BGS and Hastag differ from each other? Firstly, BGS did not have a Fourier analytic proof. They had a different proof for this one. They made 3 queries into this. They made 3 queries into this. And they made another 3 queries to check that this one. So they had, so it was, and they would do one of these 3 queries at random. This one. So it would always be a 3 query test to this property, and they got 1 minus epsilon versus some 98% or 99%. They didn't get half plus epsilon. What Hastag is going to do is going to have just one test that's going to do both the code word test and the consistency test. And what is he going to do? He's going to observe this fact that if where is pi as a function? Pi is a function from L to R. So now if I take any function in what do I want to say? I want to in the BLR representation, and we sort of did some. So the called each of this is actually a function, but we called it x. X is both an L. It's a in the long code way of writing it. It's each x is actually a function, but in the BLR way of writing it, in the dictator way of writing it, it's just a string of length 0, 1 to the n. So each thing of this is done. So what I want to look at is, if you look at x, x is a function. Where does x reside? I give you a function. I want to make this observation. I give you a function given x in 0, 1 r and pi from L to r. I want, so x is a function, x is a sort of a domain, x is a string over here. I want to say that function, I can pull it to a function over there. Then if I look at the function exo pi, I want to say this is a function on 0, 1 to the L. But what is exo pi at the 8th coordinate? It's just x of pi a. The function composition. I have a function here, and pi. I'm pulling it back to a function over here. So in some sense, every function here, is actually, if this was a valid projection. So if it's a long code, you have every function on L bits here. Here you have every function on R over here. Want to claim all these functions actually should be residing here also. If x is a function over here, x of pi should be over there, and you should give the exact same. This
So
one.
we just ignore the L minus R bits.
In some sense, you ignore it. So what Haskell will do is he's going to run a 3-query thing over here. Except one of the queries will be instead of querying it here, he'll pull it from there and think of that as a third query going to do over here. So that's going to be the test. So do the following below, the following for the triple FU, FV, and pi E. For ease of notation, I'm going to call this FG and pi. Pick x at random from 0, 1 to the L. Pick y at random from 0, 1 to the R. Pick eta from 0, 1 to the L, such that expected value of eta I is 1 minus q epsilon. It's that perturbed thing whichever we picked previously. Pick eta this way. Eta I is 0 probability 1 minus epsilon 1 probability epsilon. Z set it to be x plus, instead of I have to do y, so but instead of y we'll do y over pi. We'll pull it here plus 8. So if f of x plus g of y plus f of z.
G is pi composition. G is
No, G is shorthand for FB. Yeah. So it's going to make 3 queries here. It's going to query in this world. It's going to query x here, x plus y, y of y plus eta here, and y here. So it's going to make these 3 queries. What is so? If let's ask completeness, if I had a label cover and I honestly did the
Try to compare by x and y with y. What is the input it's going to take? It's going to take an input label on the left hand side.
no y of pi is this, y of pi is this string. So given x is 0, 1 to the r, population column. Given a, so I give you a y and a pi this way. So I'm going to define the string y of y. So it's a pullback of a string from here to a string there. And how is it? Y of pi at any coordinate a is just y at the coordinate pi a. So if you think of these not as strings but as functions, this is exactly composition. And that's the reason for using the notation y of pi. So I have to query f of x. Strictly speaking, I have to make f of x, f of y of pi, and f of c. That was the previous this one. But instead of f of, but if it were a projective, f of y of pi should actually be equal to g of y. If it were a honest to God long code encoding on both sides, f of y will be equal to f of f of y. G of y will be the same as f of y of pi.
For this, will we need that the marginal distribution of y of pi is uniform?
No. Why do? For the Haskell group, it's not uniform, certainly, because these are only some functions, not all functions. The analysis will take care of this. We'll take care of this in the analysis. So this one, you won't use black box, will not use the previous statement, because this is not, it's not true that all these 3 things are uniform. Previously, all 3 the things were uniform.
X is
uniform.
Y composed with pi is not.
This is not uniform, but this is uniform. Because no, because you're adding x and x. Yeah. Okay. Let's ask first. This is the definition. Y of pi. Let's ask completeness. Completeness should be sort of easy. That is, if there was a, if the label cover had an instance for the instance which was perfectly satisfiable, then I claim if you did the valid, if you did honest to God long code encodings and ran this PCP, it will accept the probability 1 by s. So in other words, if the completeness we are just going to, I'm not going to state it, if P is an S instance of gap 1 mu label cover and furthermore, if A going from U to L and B going from V to L, V to R. Where the colorings that witnessed. P is an S instance. Then setting FU to be the long code encoding of AU for all u in u, and FB will be the long code encoding of BB for all v in v, will ensure that probability over the random choice of uv from a choice of x, y, and eta plus p bit PCP whose FU and FP such is exactly 1 minus x.
This is true for all events, right?
This is true for every u1 v because it's
Probability you need not take over.
I need not take, but I'm just going. That's the test. The randomness of the test is this is true for every u and v. I agree, but that's the Hassler's PCP. That's the first randomness it picks. So I'm writing it over all the random response of them. I'm not going to prove this. This should be. Okay, let's start off with the soundness. What do I want to prove in the soundness? I want to prove that if there is a proof, if there is a setting of FU and FP that assesses the probability more than half plus delta, then from it I can extract a coloring which satisfies more than a mu fraction of the edges in the label color. That will say that it can't be a nonsense. Okay, if something is terribly wrong with what we've done, there is an FU and FB which will satisfy with probability more than half plus delta, but yet they need not be anything to do with the constant zero function or the constant. So here it should be the constant. I'm looking at it all as plus minus 1 world. So this is the constant 1 function in this world.
Can you modify the variables that constant skipping?
So you have now we have to do something to ensure that the constant. So he'll get. So when you're doing the soundness, so we're going to do something. We're not going to modify the predicate. We're going to modify something else. So we'll get derailed. By the all ones function. So somehow we have to ensure that the all ones function is not a function that FU and FV being all ones is never a function that is we care. So there's never be a valid input. Issue over here. So the way we incorporate this, we'll do something called folding. Notice that valid long codes. I have to now distinguish. So far, we distinguished long codes from linear functions of large support. Now we need to distinguish dictators or long codes from the constant function. So valid long code words. F from 0, 1, L to plus minus 1 satisfy F of F of x bar is minus F of x, where F of x bar is I take every bit and I flip it. The answer will flip. Certainly the constant 1 function doesn't satisfy this problem.
This is an IIT2 function.
No, but we will not do this as a test. So what we will do, so you have F of x and mine. So the whole valid long code satisfy this property. What we will assume, so what we will do in the code, what is, so this will tell you that you do not have to give me the whole table 0, 1 to the L. I will only give you half the table. The other half I will infer it. That is, for every bit, I'll only give you one of the two things. Either I'll give you x or I'll give you x bar. The other one you will invert this one. So that will come by fact that notice that's because if you look at this linear equation over here, so this is actually the product linear equation. You should have this is already in the plus 0, 1 volt, this is f of x plus this g of y plus f of z equals 0. If these were only the constraints again, certainly the all zeros function is going to satisfy. But now, every now and then, I'm not going to query f. If I have to query f of x, I'm going to query something else and negate it. So this will become a 1 minus f of x in this world. Therefore, in the plus minus world, it will become a minus f of x. So no longer will the three linear equations that I get will be homogeneous linear equations because of these things come on, and you should get that, because if I give you homogeneous linear equations, certainly it is solvable. And folding is, we'll assume the table is folded, we will run this test, but whenever we have, if x is not in the table, the equation will output will be the folded equation, will be what we infer by folding. Okay. So assume the table is folded. And there are two ways to assume it. Either you actually assume it's folded, or you give only half of it and you make the other queries. So that's the way to typically do it. But for now, we just assume the table is, you are given the whole table and it is folded.
The table is folded and only half of the labels A
will be given to you, the other half will be inferred from this.
Yes.
So folded is basically says this. You given, so you assume this table has this property, but I want to say this property is going to imply something of the Fourier curve. Assume this table is folded. That is
At I is 0.
F. So what does folding?
All even Fourier coefficients with times.
Yeah, I want to claim this will imply that for all alpha, so that if mod alpha is even, so and f is folded, f hat of alpha will be 0. Actually, we will only need it for alpha being the empty set, alpha being the all zeros code word. We'll prove it only for that case, though this is true for all cases. It should be just evident here. What is proof? The all proof should be fairly simple, no? So f hat of alpha is what is expected value of f of x and chi alpha of x. It should be evident that see a quick way of doing this. So this is also equal to expected value of f of x bar. So it's minus chi alpha of x because of flipping, which is, but because alpha is of even support, chi alpha of x and chi alpha of x bar are the same object. So this is minus f of x bar chi alpha of x bar, which forces, hence a quantity is equal to its negation, therefore it has to be 0. So this is how you get rid of the constant.
Code of alpha even then minus chi alpha of x equals chi alpha.
So what is chi alpha of x? Chi
One bar summation alpha.
alpha I xi. So firstly, if alpha, so it's only minus 1 to the power summation xi, where alpha I is
1.
1.
Yes.
So whether you sum xi is sum xi or 1, the two sums will be the same, will be of the same parity.
Okay.
That's all. Okay. Now let's end. Now we are equipped to do the soundness analysis. Assume the probability over UV to be x, y, theta. Of the 3-bit PCP accepts is greater than 1 plus delta bit. This will imply that the expectation over UV, expectation over x, y, eta of f of x, g of, so let's call it in this, let's keep this as fu of x, fb of y, fu of x plus y of pi plus eta is greater than or equal to delta. Okay. So let's do this one for at least delta by 2 fraction of edges. Okay, now for a little while, let's pick such an edge. Pick such an edge. And so we have for this edge, we have delta by 2, is less than or equal to expected value over x, y, and eta. F of x, g of y, f of x plus y of pi plus eta. Fair enough. So once again, open out. This is alpha, beta, gamma, f hat alpha, g hat beta, f hat gamma. Alpha, beta, gamma are ranging over different because one is function on 0, 1 to the L, other is function on 0, 1 to the R. That should be the one. We keep this one.
What was where did G come?
G is shorthand for FV. The AF is shorthand for FU. Right. Expectation over x, chi alpha of x, chi gamma of x times expectation over y, chi beta of y times chi gamma of y of pi. Gamma.
We can assume alpha equals to gamma.
So we can assume alpha equals gamma. So now let's do, we need to handle a few other things.
Beta and gamma are not even in the same space.
Beta and gamma are not in the same space. So let's do the first thing. So we can assume it's alpha beta. So we have f hat alpha square, g hat beta. This first thing disappears.
So 1 minus 2 beta power.
So this is chi beta y, chi gamma y of pi, and this is 1 minus 2 epsilon to the power size of alpha. This is what we have. More of this one. Let's look at what is chi gamma y of pi. What is chi gamma of y of pi? This is definition is -1 to the power summation gamma I dot y of pi I. So this is -1 to the power gamma I y pi I.
Okay, now we will.
Huh?
Gamma pi inverse.
What? So how do I want to now write this as a function. How do I write this as a function? 1 second. No, something is that's I messed up. This is fine. Oh no, this is summation over I. This is summation over I. This is summation over I in L. Am I right about that? Yes, the summation over I in L. Summation over I in L. Now notice. Let's look at the summation. Let's look at this. Actually, I should have done it over there. Okay, that's fine. So
Pi inverse, chi of pi inverse gamma of x.
I want to write this. So I want to write this as. So I want to write this more as I want to write this as -1 to the power summation j in R yj. So let's take a step back.
Gamma pi inverse theta.
Not pi inverse exactly, -1 to the power summation j in R. Okay, yj. And I have to go over all I in L such that pi of I equals j gamma I. Is that fine? But what I really care about this is not so from gamma, this summation is happening in GF2.
If it's even or
If it's even or odd. So basically, you're looking at the number of projections of a particular J, and among them, you're taking those guys and adding it GF2. So let's call this number pi 2 of, it's not exactly pi, so this number is -1 to the power yj. Let's call this pi 2 of gamma of j, where pi 2 of gamma at any coordinate j is exactly whatever I have written there. Set of I such that pi I is j. So this is what, in other words, define this. This is -1 to the power chi of pi 2 gamma of y.
That is putting this chi of chi pi to one.
Huh? Sorry. It's not pi of, it's just chi of
pi to
2 gamma of y. So if I now plug that over here, I get pi 2 gamma of y. So beta should be equal to pi.
pi to gamma.
Therefore, for all the good edges, delta by 2 is less than or equal to summation over alpha f hat alpha square g hat pi 2 of alpha is that fine? So if a test passes with probability 1 plus delta by 2, this is what we have. What I now need to show is from this encodings, I can decode a coloring. So let's now go to the task of decoding a labeling. From the proofs. So given FU 0 1 to the L to plus minus 1, FB 0 1 to the R plus minus 1. This is for all U and U, for all B and B. I want to now decode. And furthermore, we can assume that these guys are folded. The tables given to you are folded. What's a natural way to decode? What's you have? I want to from this. I want to produce a label. I want to pick up one label. So there's a very natural. So from the left hand side, you can the summation f hat square s forms a distribution. So you can pick a set yes. You can pick an alpha according to the set yes. Pick that according to this. Now you know that you're not going to pick the empty set because alpha is never going to be the folded pick. You pick some set of labels now. Alpha corresponds to a set of labels. Pick one of those labels at random. By the past argument we had shown, by at least the intuition from the long code coding is most of these things, the Fourier coefficients are going to be concentrated on short response. Of course, this was before we did the consistency test. But if we believe everything was right, most of the weight is going to be on alphas of small weight.
I think that expression is also, we can infer a statement like that.
From this directly. That's what we are going to do. We are going to do that right away from this. So the labeling. So define randomized labelings. A from U to L and B from V to L, V to R as follows. A is just this. For each U and U. Just AU, I define AU. AU is first pick alpha from 0 1 to the L with probability f hat u square of alpha. Pick a random A in the support of F. Similarly, notice this is never going to return, and this is never going to because it's folded. You will never going to you're never going to run into issue. You will never pick an empty set. You will never pick alpha with the you will never pick alpha which is the all zeros function. So here.
So here with what you mean, so you're going to think of it as a linear. What does support of alpha mean?
Alpha
Alpha, I see. You mean alpha there.
Alpha there, so it's a referring to coordinates. Yeah, and to be more formal, but it should be clear what I mean there. It is so certain coordinates, it's picking it up, and I'll pick one of those coordinates at random. Now let's.
So we will sample it from G at alpha or A at alpha.
It will satisfy from FB G at to the corresponding G and do the same thing.
But
so let's
expression we don't have G hat beta square, we only had.
That is true, that is true. So that's, we'll have to do, it's not, thing is not going to pick beta from 0, 1 to the R with support f hat v square of beta to pick a random b in support beta. So let's just ask us what's probability over UV and this choice of AB, that is pi E of AU equals BB. Let's ask, we have done this decoding, what's the probability that you are actually going to so what's the lower bound we can put on this object?
When you have put it is.
Hmm?
When is that?
No, I have this. No, so I want to say this is at least. I don't want to arithmetize it. I want to just say overall alpha. So how do I want to pick this up? I pick up an alpha such that, and probably I pick that alpha as f hat square u of alpha. Then I pick a beta such that beta is fully contained in alpha. So f hat square v of beta.
Why is beta contained?
So I'm just putting a lower bound on this object. So I want to claim this. I want to claim 1 by support alpha. This is a lower bound is what I want to claim. So you could have picked. So let's focus on a particular. This is randomized over there. Then there's an expectation on this. Do you buy this? This is for that particular edge. What's the probability that I pick an alpha beta pair so that beta is contained in alpha? That's just the summation over alpha beta f hat square alpha f hat square this beta. That's just the probability I pick that pair. Now for beta I could have picked any guy over there. So for every such guy there is at least one element in alpha because I have chosen beta. Sorry, not
support beta.
not beta. So I should have picked beta in pi of alpha. So alpha think of it as a bunch of labels. Pi of alpha is a now bunch of labels in R. Beta is one such object. So now no matter which beta I pick up, there is at least one guy in alpha that there's no support alpha, it's size of alpha. I don't know why I'm calling the cardinality of alpha. That's just called it. Not there. Yeah. Oh, I'm very fast, man. Let's finish this off. We are almost done. All of these actually I just call them size of alpha, size of beta. This should be clear from what we have done so far. Okay. Is this expression clear? Yes.
Sorry, what is beta in pi of alpha?
So alpha now alpha was viewed as a 0, 1 to the L. And I need pi of alpha. This is sort of a, so I'm,
So you're looking at the.
but alpha now I'm not viewing it as a, I'm viewing it, I view alpha as an indicator of labels. Then apply projection on those labels and get the corresponding indicator function. On R's.
So these are basically, so what you're picking here are valid alpha beta, like valid pairs that will satisfy the pi constraint on the edge. If we look at this summation, all the alpha betas that appear.
But alpha betas don't set. Alpha is a set of labels, beta is a set of labels.
Yeah, this type change.
Isn't it an exact equal
Which one?
this right hand side? Because beta, okay, no, beta is not resistant.
No. So there's a fact that there's a type. So alpha so far was viewed as a string in 0, 1 to the L. View this as the indicator function of a set. Now, and alpha refers to that set. Apply pi on that set. You get an indicator function. This one and B, when I mean, and beta when viewed as a set is a subset of that set. Yeah, there are two operations, but this is what.
And we want to show this, right? We want to show this greater than.
No. This by that process, this is clear. This should be clear because the property of being such an alpha beta is exactly this quantity. By this one. Now, in that B, once I pick such an alpha beta, the problem I could have picked any element in B in beta. Every such element will have a pre-image in A because the way nature I picked alpha beta pair. Therefore, what's the probability that I picked that pre-image? It's at least 1 over alpha. There might be more than one pre-image, so it's at least 1 over alpha. Therefore, with this probability, the edge will be satisfied. And what we will now show is this quantity for all the good edges. We have something like this. So basically, for the good edge, for good edges, which are delta by 2 in fraction, we know that, what do we know? We know that summation f hat square alpha g hat square g hat by 2 beta into 1 minus f2 epsilon size of alpha is at least delta by 2. This is what we have. But if I had this expression, exact same expression over there, I would have been done. I don't have it. So now I need to relate. So we need to relate. Summation alpha f hat square alpha f hat square alpha summation beta in pi of alpha g hat square beta 1 over alpha to the above quantity. I need to show that this is bounded from below if that is bounded from below. Yeah, so let's just do a bunch of calculations now. This will be. And then I'm going to, so for a good alpha, for a good edge, summation alpha, summation beta in pi of alpha, f hat square alpha, g hat square beta, 1 over alpha. B hat square. This is at least summation alpha, f hat square alpha, g hat square pi 2 alpha, 1 over alpha. Because pi 2 alpha is one of these sets.
So what is pi 2 alpha?
Pi 2 alpha is you summed the pre-images, and if the sum was even odd, you put a 1. This is one of the subsets of this pair. So now the point is the expression which we have has 2 and 1. It has it's f hat square alpha g hat, whereas this had f hat square alpha g hat square this one. So ideally, I would like to get it to that expression. I need to bound it to that expression. So let's see if I can get the square of that expression. So to get the square of that, typically I need another f hat square alpha. And that I have Parseval will give me. So I could just multiply this by summation alpha f hat square alpha.
So it's a couple of body parts.
It's going to be a couple of Cauchy-Schwarz and various things. Yes. So what I will do is this is certainly greater than or equal to alpha f hat square alpha g hat square pi 2 beta 1 over mod alpha. This whole thing summation alpha f hat square alpha. Is that okay?
The x plus by 2 alpha.
Equal.
This is equality. No, I only need. This is all. I'm not going to add the other one. So then this is greater than or equal to summation over alpha f hat square alpha g hat by 2 beta over 1 over square root size of alpha the whole square. That's Cauchy-Schwarz. This is almost what we want, except this is 1 over square root alpha, that's 1 minus 2 epsilon to the power alpha. Notice, at this point, you should almost have got it. This is a polynomial in size of alpha, that's exponential in size of alpha. So certainly this should be larger than that. Question is what you want to set it up, and you can, it's not hard to see that this is larger than the right. If you do the, I'm just going to use the inequality that 1 by root z is larger than square root 4 epsilon into 1 minus 2 epsilon to the power z. So this is 4 epsilon into summation alpha f hat square alpha g pi 2 beta 1 minus 2 epsilon to the power size. This is, you can get that from Taylor series. I'm not going to do it. For every epsilon. Therefore, this is 4 epsilon. There's a square here. Delta by 2. So for at least delta by 2 fraction of edges, this is satisfied. Therefore, probability over UB and AB phi of AU equals BB is at least delta cube epsilon by 2. So you choose your mu to be, the label cover mu to be this smaller than this. So what's the label cover mu? So if you setting, so if you choose mu to be delta cube epsilon by 2, then P is not a noise.
Is this the same as giving alphabet reduction scale?
No, this is not the noise value. No, this is not alphabet reduction. This is
And because in 1 by 1 new level over here on alphabet and here it will be simplified.
no, in some sense it is alphabet reduction. Then we would also do this alphabet reduction. This is composition. This is exactly what we did as PCP composition, reducing it to a smaller alphabet size. Yeah, and that's the end of. Okay. By the way, we have max free ln. I want to say because we have max free ln 1 minus epsilon half plus delta, we also have max free sat. A 3 ln can be written natural way as a 3 sat instance. What's a natural way to write a 3 ln? So hence, at the end of this, we have got that gap 1 minus epsilon half plus delta 3 ln 2 is NP hard. Now to go to max 3 sat. So just the reduction, if you have X or Y or Z equals B. So let's just look at it as 0.
You should get 7 by 8.
Yeah, but wait. So what's the, I can write this as X or Y or Z equals X also, this is what I want to write. The parity, yes. I'm going to put 4 clauses. When I write parity as
Yeah, you can always write this. Sure. So you want to accept on odd weights or even weights.
that's what I'm doing right now. So replace that one tree-learn statement with these 4 preset statements.
Even weight, you will.
I mess it up or. So I want to say if that is satisfied, all the 4 are satisfied.
So that is satisfied on.
That is satisfied on even weight strings. So should I actually make it simpler for me and write the odd weight thing which I'm more comfortable with? So equals 1. This is the same as X or Y or Z. X or Y or so pick up always 2 guys. So I think that one is exactly this. So replace the parity. Huh?
You just negate the and.
Yeah, but you need the DNF for this one. They give you the other 4 clauses. Exactly the other 4. So replace every 3len 2 with 4 3CNF statements. Now, if it's satisfied with 1 minus epsilon probability, this will also be satisfied with 1 minus epsilon probability because all the 1 minus epsilon will be satisfied. It's half plus delta. The half plus delta is each one of them, 3 of them will be 3 out of 4 will be satisfied. So 1 minus epsilon will go to 1 minus epsilon into 1, and I don't care about the rest, that is 1 minus epsilon. The half plus delta possibly go to 3 out of 4.
7 by 8 plus 3 by 4.
And half minus delta possibly go all the way to 1. And what is that?
3 by 8 plus half. 7 by 8 plus 3 delta by 4.
3 by 8 plus 4 by 8, no? So 7 by 8 plus
7 by 8 minus delta by
Minus delta by 4.
it cannot be a minus delta.
plus delta.
Huh?
Plus delta.
Why am I getting minus delta by 4?
They need a stronger introduction.
Hmm?
They need a stronger introduction.
Why do I need a stronger reduction?
You should get to more than 7 by 8.
No. So what am I doing wrong over here? I should get a plus delta by 4 here. When am I messing it up? Sorry, this is going to get multiplied by 1 and this is going to get multiplied, which is exactly 1. Yeah. Those are the guys I satisfy, those are the guys I don't satisfy. So this will be the, except for a cat, This doesn't give you three sat with perfect completeness. Only tells you distinguish 1 minus epsilon 3 sat from 7 by 8 plus delta by 4 3 sat is NP hard. So if you run this reduction, you get that corollary is gap 1 minus epsilon 7 by 8 plus delta 3 sat is NP hard for every this one. But Hastad in his paper, he actually proved the stronger statement also. He proved that you don't need 1 minus epsilon, you can actually get 1. But that requires more, it's not it requires a tailor-made PCP for it, not a reduction from 3lin. 3lin you can't expect better, but for 3 sat you can, and he gives another. Okay, let's stop with this, and next lecture we will see how to extend these to we'll basically introduce unique games and see how to extend this, why this label cover is insufficient, and if we had a little more, why it will imply unique games, and so in particular max cut and vertex cover. Let's stop.